Okay, so today we are going to revise week 7 and week 8 topics. All right. Okay, so in week 7, we have inner product spaces defined for Rn and Cn in general. Right. So, how are inner products defined for Rn or Cn? So, the Euclidean inner product, if you take any two vectors in Cn, then you see that the inner product is defined in this way: u1 v1 bar plus etc un vn bar. So if it is Rn, there is no complex conjugate. For Cn, for the second part, you have the complex conjugate, right? And what are the properties we have for this inner product? So inner product v comma v is always non-negative, and it is equal to 0 if and only if v is 0. Only when v is 0, the inner product of the inner product v comma v will become 0. Okay, and you see that it is linear with respect to the first variable, right? And conjugate symmetry is there. It means what? Inner product u comma v is same as inner product v comma u bar. Okay, so what are the other properties? Inner product of any vector with the zero vector is always 0, right? And with respect to second variable, we have additive property, but when it comes to scaling, the scalar comes out with a complex conjugate. Okay, so these are some basic properties of inner product defined on Cn. Okay, so the next thing is norm. What is norm? Norm is something which tells the distance of a vector from the origin, right? So here you see that norm is a non-negative real number, right? And it is defined as positive square root of inner product v comma v. Okay, so always remember that we know that inner product v comma v is non-negative, so this is defined for us, right? So for example, if you have a vector like this, how do we do the inner product? So here you see that this is your v1, this is your v1, v2, v3, right? So here you see that v1 v1 bar plus v2 v2 bar plus v3 v3 bar, right? Because this is inner product of v comma v, right? So that is what we are doing here, right? And what is I bar? I bar is minus I, 2I bar is minus 2I plus 3 comma 3. For real numbers, complex conjugate does not affect anything, right? So this is the answer. So usually this is how we compute norm of any vectors, right? Okay, so now a vector, suppose there is a vector for which the norm is 0, then it means that the vector itself is 0 because of this property here, that inner product is 0 if and only if v is 0, right? And scaling, norm lambda v is modulus of lambda times norm v. So when lambda comes out of the modulus, it comes as comes out of the norm, it comes out with the modulus. Why? Because you know that norm is always a positive number, non-negative number. So when you take out a scalar outside the norm, you have a modulus sign here. All right. Okay. So now what are orthogonal vectors? So when you take two vectors and take the inner product, if it is 0, then we call such vectors to be orthogonal. You remember in R2, any two perpendicular vectors are orthogonal, right? For example, if you take 1, 0 and 0, 1, they are orthogonal, right? So inner product u comma v or v comma u, both should be 0 because you see that conjugate symmetry property is there. So u perpendicular to v or v perpendicular to u are same, right? Okay, so if you see that 0 vector is orthogonal to all vectors, you take any vector, 0 is orthogonal to it because inner product 0 comma v is 0. Okay, what is the only vector which is perpendicular to itself? The 0 vector. No other vector can be perpendicular to itself, right? Okay, so what is orthogonal decomposition of a vector? Suppose you are having two vectors u comma v within Fn, okay, and v is non-zero, then we can write u as cv plus w. What is this c? C is given in this way, where this is inner product u comma v by norm v square, and w is equal to c minus u minus cv. Okay, so this w is orthogonal to w, sorry, v. Okay, so here you see that some background here projection is involved, but let's not go into the details now. Let's just revise what are the topics and do some specific problems. Okay, so let us concentrate on just the important topics and specific problems because we are revising for the exam. Let's not go into the background concepts here. Okay, fine. So you see this inequality, these two are used sometimes to solve problems. So this is the Cauchy-Schwarz inequality and this is the triangle inequality, right? So Cauchy-Schwarz inequality, you see we are relating a inner product with the norm, and here triangle inequality is about the norm itself. Okay, and what is parallelogram inequality? Actually parallelogram, it is equality I should say. So for u comma v in fn, norm u plus v whole square plus norm u minus v whole square is equal to 2 times of norm u square plus norm v square. Okay, so norm of u plus v whole square plus norm of u minus v whole square is same as 2 times of norm u square plus norm v square. Okay, fine. Now let us do some problem. Find all vectors in R3 which are orthogonal to both 1 comma 1 comma 0 and 0 comma 0 0 comma 1 comma 1. How to do this? We want to find all the vectors orthogonal to this. So do we have any name for this? So let us say for the first problem, so suppose you consider W to be the span of these two vectors. What is the set of all vectors orthogonal to these vectors called? Can you tell? It is called the orthogonal complement, right? Yeah. Okay. So you see that. So let us say you have a vector x comma y comma z in R3 such that inner product x comma y comma z with 1 comma 1 comma 0, right? This is 0, right? And inner product x comma y comma z comma 0 comma 1 comma 1, this is 0, right? So you see that we are finding vectors which are orthogonal to both the vectors. So I'm taking a random vector and I'm saying that suppose if it is orthogonal to both the vectors, how it is going to look, I'm going to check. Okay, so you see that when I do the inner product, what will I get? X plus y is equal to 0, and here I get y plus z is equal to 0, right? So this means what you are getting here, x is equal to minus y, z is equal to minus y, right? So what is the set you are getting? Minus y, y, minus y, y in R. So this is the set of all vectors orthogonal to, let's call this, maybe let's give this some name, v1 v2. Okay, to v1 and v2. Okay, so just also to know that suppose let's say w is equal to span of v1 v2, then w perp is this span of which vector? Can you tell me? What is the vector I can write here? Can you tell me? W perp is the span of,
minus 1 1 comma minus 1.
yeah. Okay, fine. Right. Next example, let us see. So the next example is that, so now we are in C3, so you should use the corresponding inner product. So you have two vectors. Let's do the same process. So let x comma y comma z in C3. Okay, so now you have inner product of x comma y comma z with 1 comma I comma 0 is 0, and inner product of x comma y comma z with 0 comma I comma 1 is 0. Now you have x plus iy is 0, and y, sorry, here it is 1, not I. Someone asking something?
Yeah, ma'am, minus I y, no? Because in complex then we
Okay,
have
okay,
to
yes, thanks for pointing out. So here you have x plus I bar y, right? So x plus I bar y, so it means you have x minus iy equal to 0. Yes. And here you have I bar y plus z is equal to 0, right? So here minus iy plus z is equal to 0, right? So you have x is equal to iy and z is equal to iy, right? So now what is the set of all vectors orthogonal to these two vectors v1 and v2? Iy, y, iy, right? So y in R. So now what can you, y in C. So now what can you say about this? What is the spanning vector for this, or let us simply write what is the spanning vector here? What is the spanning vector here?
I1 comma
Yeah, this is the spanning vector. Okay, fine. Yeah, sorry for the interruption. Yeah, so this is how we compute the orthogonal set of vectors for any given vectors. Okay. Now suppose you are, so in both the cases we are having two vectors. Suppose you are finding all vectors orthogonal to one vector, then how many vectors will you get in the spanning set? Can you tell? See, notice one thing, that here dimension of w plus dimension of w per is the, so here if it is rn or cn, if it is rn or cn, okay, then here it is n. Okay, so in our case what is n? In our case n is 3. So since dimension of W is 2, you have two linearly independent vectors. You see the dimension of W perp is 1. Right? Now, what should be the dimension of W perp if W has only one vector? Tell me.
2.
What's the answer? Yeah, the dimension of W perp should be 2. Right? So in that case, you will have two vectors. For example, suppose you want to find, let us say W is equal to span of, for example, very simple case I'm telling, 1 0 0, right? What will be the spanning, or maybe not so trivial, maybe 1 1 0 I'll take, just for you to understand. Then what will you do? You take inner product x comma y comma z with 1 comma 1 comma 0 and equate it to 0. So the resulting thing is a plane x comma x plus y is equal to 0, right? This means you are getting x comma minus x comma z in R. So this is your W perp, right? So you will get two vectors which are spanning this, right? So it is span of 1 comma minus 1 comma 0 and 0 comma 0 comma 1. So you see you have two vectors now. Clear? Right? So you can understand how many vectors you will have in the spanning set from the dimension of the W you are considering. Okay, is it clear? Fine. So next, suppose you are given a set of vectors in F1, we say it to be orthonormal if inner product Vi comma Vj is first of all 0. It should be first of all orthogonal, and also the norm should be 1 for I is equal to 1 to k. Okay, inner product Vi comma Vj is 0 for I not equal to j, and norm Vi is 1 for I equal to 1 to k. Okay, if V1, V2, Vk are orthonormal, then they are linearly independent. Okay, if V1, V2, Vk are orthonormal, they are linearly independent. How can we see this in R2? I'll just say in R2, you can visualize it and remember it for general space. See, for linear independence, do you remember I told you that if two vectors are in different directions, okay, any different direction, then they are linearly independent. Now orthogonal means you know that they are actually in exactly at 90 degree. For example, in R2 I'm talking, right? So in that case, you see, definitely obviously they are in different directions, so they are linearly independent. So orthonormal or just orthogonal, even if you just have orthogonal, then also you will have linear independence. Orthogonal implies linear independence. Okay, fine. So if you have a set of orthonormal vectors, then this condition is satisfied. Okay, so these are some properties. Okay, fine. And when will we call a basis to be an orthonormal basis? If the vectors are orthonormal. That's all. Right? Okay. Do you remember how do we usually compute the coefficients if you are given a different basis other than the canonical basis? For example, in R2, suppose you have a basis like this. Okay, and you want to express some vector 2 comma 3 as alpha times of 1 comma 1 plus beta times of 1 comma 0. How do you compute alpha beta? How to find alpha beta? Can anyone tell? How do you find alpha beta?
Ma'am, we just multiply and equate them
Yes,
with
you
equations.
yes, you have to solve the system, right? So you have a system of linear equation, that is here alpha plus beta equal to 2 and alpha minus beta, sorry, not alpha minus beta, just alpha is equal to 3, right? So you have the system, then you solve this and write the equation. Okay, and whatever is the basis, you have this process, you have to solve a system of linear equation. In this case it is quite simple. Suppose you have some other complicated example, then you have to actually do this kind of a process, right? But when you have an orthonormal basis, the process is very very much simplified. Okay, you don't have to do any kind of operations like this. It is very easy. How to find alpha? Your alpha will be simply inner product v comma v1, and beta is simply inner product v comma v2. You don't have to solve anything. If you have an orthonormal basis, you can simply write inner product v comma v1 as alpha and inner product v comma v2 as beta. Okay, so that is the advantage of having an orthonormal basis. Clear? Okay. So it means we should know how to get an orthonormal basis, right? So to get an orthonormal basis, we have what is called the Gram-Schmidt process. Okay, what is a Gram-Schmidt process? Gram-Schmidt process converts a given set of linearly independent vectors to a set of orthonormal vectors. Okay, so suppose you have a set of linearly independent vectors v1, v2, vk, then you apply this formula to get a set of orthonormal vectors. Okay, so let us do one example for this. So let us say you have these vectors here. Let us call them the same notations we use. So let us call them v1, v2, v3. What is the first step here? So step 1, for step 1, what is that? U1 is equal to V1 by norm V1. U1 is equal to V1 by norm V1. What is norm V1? Tell me quickly.
Root 3.
Yeah. So you have 1 by root 3 times 1, 1, 1. So this is your U1, right? Now what is step 2? So in step 2, what is that formula you have? So you have W2 is equal to Vj. What is Vj here?
V2.
V2 minus inner product of V2 here U1 U1. Okay, inner product of V2 U1 U1. Okay, inner product of V2 U1 U1, and the remaining terms will not be here for W2, right? So now let's calculate this and see what is that we are getting. So what is your V2? V2 is 101, right? And what is inner product of V2 U1? So your V2 is 101 and U1 is 1 by root 3, 1 by root 3, 1 by root 3. Again, you have to multiply it 1 by root 3, 1 by root 3, 1 by root 3. Okay, so no, the bracket comes before. So yeah, so you see that you have 101 minus, now let's first do this inner product. You will get 1 by root 3 plus 1 by root 3, which is 2 by root 3. 2 by root 3 times of this vector 1 by root 3, 1 by root 3, 1 by root 3. So now if you multiply this inside, you will get 1 comma 0 comma 1 minus 2 by 3, 2 by 3, 2 by 3. So now if you subtract, what will you get? What is the resulting vector? 1 minus 2 by 3 is 1 by 3.
1 by 3 is Z.
1 by 3 minus 2 by 3 and again 1 by 3. Right? So this is the resulting vector. Now what is the next step? So you need to normalize this. So for finding U2, you have to take W2 by norm W2. Everyone quickly calculate the norm of W2 and tell me. Calculate the norm of W2. What is the norm? Is it that difficult?
Root 5 by 3 maybe.
Root 5 or 6?
Root 6 by 3.
Root 6 by
Oh,
3,
sorry,
right?
6. Yeah.
Yeah. So norm W2 is root 6 by 3. Okay. So now if you want to calculate U2, then you have to consider what is your W2. This is your W2. So you have root 6 by 3 the denominator. So if root 6 by 3 is there in the denominator, it will become 3 by root 6. And then you have 1 by 3 minus 2 by 3 and 1 by 3. Right? So you have 1 by root 6 times of 1 comma minus 2 comma 1. Okay. So we have obtained the second vector. Now what is the third vector? So the third vector, what is the formula? W3 equal to V3 minus inner product of, here again, V3 comma U2 minus, again what will you get? V3 comma,
U1.
yeah, U1. Okay, so now let's do this and see what you are getting. So for V3, what is the vector? 0, 1, minus 1. 0, 1, minus 1. Now what is inner product of 0, 1, minus 1 with 1 by root 6 minus 2 by root 6, 1 by root 6 times 1 by root 6 minus 2 by root 6, 1 by root 6 minus your V3 is again 0 comma 1 comma minus 1 and U1 is 1 by root 3, 1 by root 3, 1 by root 3. Okay, so now you have to compute it. What will you get if you do this inner product here? 0 comma 1 comma minus 1 minus, what is this? The first one becomes 0. So you have minus 2 minus 1 by root 6, right? So maybe we'll write it as minus into minus, it becomes plus. So let's write it as plus 3 by root 6 of 1 by root 6 minus 2 by root 6, 1 by root 6. Right? And then here you have 1 by root 3 minus 1 by root 3. So this becomes 0. This inner product is 0. Right? So you have only this part. So you will get 0 comma 1 comma minus 1 plus 3 by 6 minus 6 by 6 minus 3 by 6. Sorry, comma 3 by 6. So you have 0 comma 0 plus 1 by 2 and here minus 1. So this is 0 and here you have minus 1 plus 1 by 2. So minus 1 by 2. Okay. And so what is your U3 then? Tell me what is your U3? U3 is equal to W3 by norm W3. What is norm W3? Compute and tell me quickly. Compute it
1
and
by
tell
2.
1 by 2.
1 by root 2.
1 by root 2. What is the correct answer? Okay. So for norm,
1 by 2.
4 plus 1 by 4. So square root of 2 by 4. So square 1 by root 2, right?
Yes.
Okay. So this means now what we have to do? We have to simply multiply with root 2. So you have 1 by root 2, 0 minus 1 by root 2. Okay, so this is your U3. So first let us compare your U1 with U3. So what was your U1 if you remember? Can you tell me? So U1 was 1 by root 3, 1 comma 1 comma 1. So if you multiply it with this, what will you get? What is inner product of U1, U3? Quickly.
1 by root 6. Uh, No?
Should be 0, right?
Yes, ma'am.
What is u2? If you remember, u2 was yeah, 1 by root 6, 1 minus 2, 1. Now what is inner product u1 u2? U1 and u2. What is the inner product? So you keep the constants outside. So you have 1 by root 3, or if you want you can multiply also, does not matter. So 1 by root 18. So whatever you multiply, just quickly calculate and tell me, is it 0 or not? You calculate. I don't want to calculate every time. It should be 0, right?
Yes, ma'am.
Yes. Now what is inner product? U2 U3. This is your U3. What is inner product of U2 with U3?
0.
0. Also you can notice that norm U1, norm U2, norm U3 all are 1. This also you can verify. It means what? We have obtained an orthonormal basis, and that is nothing but U1, U2, U3. So this U1, U2, U3 is the orthonormal basis which we have obtained. Clear? How to apply Gram-Schmidt process? Is it clear for everyone? Yeah? Okay.
Yes.
So for every subspace Fn of Fn, we can have an orthonormal basis. There exists an orthonormal basis. Okay, and for any operator T from Cn to Cn, there exists an orthonormal basis with respect to which the matrix of T is upper triangular. Okay, so this is Schur's theorem. Okay, so now what are orthogonal complements? Already I used this notation earlier, right? So it is the collection of all orthogonal vectors to S. So if you are considering a set S, a subspace S, then you can collect all the vectors which are orthogonal to all the vectors of S. Then that is called the orthogonal complement. Okay, fine. So now what is the important property about orthogonal complement we will be using? S perp is a subspace. Okay, so just like S perp is also a subspace, and the intersection S perp is always 0. Only the 0 vector can be there in the intersection. Okay, because why is that so? Because suppose let us say you have a vector v in S intersection S perp, then you should have v comma v equal to 0. But when is this possible? It is possible only when v is 0, right? Okay, so what are the other properties? We see that dimension of S perp is equal to n minus k. So this I already told you, right? Dimension of S plus dimension of S perp is equal to n, right? And S perp, the whole perp, is equal to S. If you are going to take the complement wise, then it gives back you the original set. Okay, so these are some important properties of complement of a subspace, and we have already seen examples for this, right? So the next important topic here is least square solution. Okay, so what is least square solution? So suppose let us say Ax is equal to B. Okay, so Ax is equal to B. This is the system. So if that system already has a solution, the least square solution is just the solution of the system. But suppose it does not have a solution, then only we are looking at what is the least square solution. It's kind of an approximate solution. Okay, so what is the best approximate solution? That is what is called as least square solution. Okay, to find the least square solution of a linear equation Ax is equal to B, we have to solve this equation. AHA x star is equal to AHB. Okay, so let us look at some examples for this. So now you have a matrix 1, 2, 2, 4, 1, 1. So this is your A, this is your B. Okay, so what is your AH then? What is AH? What is the conjugate transpose of this matrix? It is a real matrix. So AH is same as A transpose. What is the transpose of this matrix?
Same.
Yes, 1, 2, 2, 4. Right? So multiply AH with A. What is that you will get? Compute and tell me. Compute and tell me the resulting matrix.
Five, 12, 12, 20.
5,
12,
12.
12, 20. Yeah.
2 plus 8 is 10, right? 5, 10, 10, and then 4, 20. 5, 10, 10, 20. Please make sure your calculations are correct. I guess this is the correct answer. Does
Yeah,
anyone
yeah. So
agree with?
yeah, yeah, it's fine.
Yeah, fine. Okay. So now the next thing is we need to find the RHS, which is AHB. So you have to compute 1224 times 11. What is the answer? 3, 6. Right? So you have 3, 6. Now we are going to look at the equation 5, 10, 10, 20, x1, x2, 3, 6. So do we have a solution for this system? What is the system first of all? 5x1 plus 10x2 is equal to 3. 10x1 plus 20x2 is equal to 6. So twice the first equation is the second one, right? Now you see that, so both equations are the same except for the multiple. So you can just consider 1. 5x1 plus 10x2 equal to 3. So how do you find solution if you have two variables and one equation? Yeah. So suppose if you are putting, for example, x1 is equal to 1, then what should be your x2? If x1 is equal to 1, what should be your x2? So you have 10x2 is equal to 3 minus 5, which is minus 2. So x2 is equal to minus 1 by 5, right? So you have a solution which is of the form 1 comma minus 1 by 5, or if you just want whole numbers here, you can replace with 5 comma minus 1. So you put 5 here and minus 1 here. Does it work? 25 minus 10. No, I made some mistake, I guess. What was the mistake? What was the error? Can anyone check? 10x2 is equal to 3 minus 5 minus 2. 2 5s are 10. So I took 1 comma 1 by 5. 5 comma minus 5 5s are 25. 25 minus 10. What is the error here? I don't see an error here. What is the error?
If you are multiplying the entire thing, so 3 also get multiplied with 5, right? So 15.
Okay, we are not looking at this equation here. See, 5 comma, you are saying you are multiplying 3 also with 5. Is that what you are saying?
Yes, ma'am.
Yes, yes. So if you are just putting 1 comma minus 1 by 5, then what happens? If you are just putting 1 comma minus 1 by 5, then you are getting actually 5 minus 2, which is 3. Right? When I'm doing this multiplication, this also gets multiplied. Yeah, so be careful while doing this. I made this error. So be careful while doing this. Yeah. So you see that the span of this set is your solution. What is the least square solution? The span of this set. or in fact you can specifically say instead of span, this is your least square solution, 1 comma minus 1 by 5. Not
But
span,
it
just
has multiple solutions, right? But how do we select this? Even if I use x1 equal to 2, it will give different result, right?
yes. So if you want to just consider all the multiples, then you have to be careful with what is the solution here. So because it gets multiplied here, usually that so you cannot here, if you are writing it as a span, then it is just a product and then you get an error. So how should I write here the set of all solutions? This is one least square solution I can see, but how to write the set of all solutions in this case?
So like x1 equal to, right, 3 minus x2,
So I
right?
can write k, yeah, what?
No, I mean, you can write x1 in terms of x2, right? Then x1 comma whatever the expression
So
for x.
usually what is done is that you take x1 is equal to t and then you write t comma, here you write in place of x2 you write 3 minus 10, sorry, not 10, 5t by 10.
Correct.
So if you write like this, then there will not be any error. So if you can write it in this way if you want. So here you have t times of or you cannot take out t in this case. Yeah. So just like this you can write. Yeah. So
Yeah, ma'am,
this
we
is,
can just
yeah. So this is the set of all least square solution. Okay. So the same way we can do the second problem as well. Only difference in the second case is that now you are, what is the size of the matrix in the second case? What is the matrix? It is a 3 by 2 matrix, right? So since it is a 3 by 2 matrix, what will be the order of AHA? What is the first of all order of AH? It is 2 cross 3. So what is the order of AHA?
3 cross 3.
See, AH is first and A is next.
So 2
2
cross.
cross.
Yeah, this is also 2
2 plus
cross 2.
2.
Yeah. Okay. So now let's compute it. So you have A is equal to 101101. 101101. Now what is AH? AH is 101101. Written as columns. Okay. Now what is AHA? Compute and tell me. Compute AHA and tell me the matrix.
Two one one one
211.
one.
1. Are you sure the last one is 1?
Ma'am, it should be 2.
Yeah. Okay. Fine. Now the next thing is that you have to compute AH times B. Here B is 111, I guess. 3 ones. Yeah. So compute AHB. So you have 110011 multiplied with 111, which is 2,
Comma 2.
right? So now we have to solve 2112 x1 x2 22. So now what is the equation? You get 2x1 plus x2 equal to 2 and x1 plus 2x2 equal to 2, right? So now we can call this equation 1, call this equation 2. Let's do 1 minus 2 times of 2. If you do this, what will you get? You will get x2 minus 4x2, which is equal to 2 minus 4. So you get minus 3x2 equal to minus 2. Is that correct? Yeah.
Yes, ma'am.
So do we get x2 is equal to minus 2 by 3? Yeah, x2 is equal to 2 by 3. So compute x1 quickly and tell me the answer. What is x1? Compute and tell me what is x1.
3/2.
Sure. Check again.
2 by 3.
2 by 3.
It's 2 by 3. Right? So you can verify it from the equation. 2 times of 2 by 3 plus 2 by 3 is 4 by 3 plus 2 by 3. So you have 6 by 3, which is 2. Okay. So you have a unique solution in this case. Okay. Fine. So this is how you find least square solution. Okay. Fine. So the next topic is what are projections? Okay. So projections are again very important. What are projections? Suppose let us say you have a subspace S of Fn whose dimension is K. So a projection of Fn on S means you have what is the range of PS. All the elements from Fn are mapped to S. A projection map will take all the elements of Fn to S. Right? So for example, suppose I'm going to do my S is, let us say, the x-axis. The set of all x comma 0, x is in R. Okay? I'm considering the x-axis as my S. So this is my S. Okay. So I'm going to project any vector x comma y. I'm going to project any vector x comma y onto S. So what is that mapping? So it is going to be projected on this point x comma 0. So you see any x comma y is mapped to x comma 0. So this is a projection, right? So orthogonal projection, perpendicular projection, right? So the range is the space S. And what is the null space? Null space is the S perp, right? So it means what? What is the orthogonal complement of this S? This is your S perp now. So this is your S perp. Y-axis is your S perp, right? So all the elements on y-axis will get mapped to origin, right? All the elements on y-axis, when you project on x-axis, it is mapped to origin. That is why the null space of PS is S perp, right? And PS square, and here the same is actually given in this way. So for any vector u in S, PSU is again u only, because you are going to project on the same vector. And for any vector in the S perp, it is 0, because the null space of PS is S perp, right? And the projection has this property that PS square is equal to PS. It is because of this again, right? So you have PS of PSU again. So you have for any element V, PSV is again in S, right? So when you project, you are going to get back the same vector. Okay, so you see that we have all the five properties for projection. So these 5 properties you definitely need to remember if you have if you want projection if you want to answer any questions on projection. Okay, fine. So now suppose, let us say, just a simple question, let me ask. Let us say you have a subspace W. Okay, so you have PW is the projection of R3 onto W. Okay, so this is an orthogonal projection. Now can you tell me what is P of 1 comma minus 2 comma 1? Can you tell me what is it?
Is it same? One
Yes.
comma minus 2.
Yes, right? Because you see that 1 comma minus 2 comma 1 belongs to W. So if it is in the same space, projection will be on the same, right? Same way, if you take anything from the orthogonal, sorry,
So we
anything
need to
from,
verify that 1 minus 2 comma 1 is in that plane, right? So that
exactly.
should satisfy. Then only we can say this. Okay.
Yes, yes. Okay, fine. So what is the range of this projection? What is the range of this projection?
3.
Range. What is the range of this projection?
1. Right.
Look at this here. Look at the properties here and answer. What is range of PW?
Range of subspace.
Just look at the properties here and tell me. It's already given.
Yeah. Same as subspace.
Yes. The range of PW is W. Now what is the null of PW?
W prep.
What is W perp here? Can you quickly find it? So the spanning vectors, you need some spanning vectors here, right? So maybe you can take the spanning vectors as 1 minus 1 0, 0 1 minus 1. Okay, so these are spanning vectors for this. So W is equal to span of these two vectors. Do you agree? I just quickly saw it and wrote it. So 1 minus 1 is 0, 1 minus 1 is 0. They are linearly independent, so they form a basis. So what is there in W perp? So x minus y is equal to 0, y minus z is equal to 0. So x is equal to y is equal to z. So x is equal to y is equal to z. So it is a span of 1 comma 1 comma 1. Right? So you multiply 1 comma 1 comma 1 with any of this vector, you will get 0. Right? So you see that W perp is this span of 1 1 1. Okay? Fine. Okay, now let's move on to topics in week 8. In week 8, mainly we look at operators and inner product spaces, particularly adjoint, and then we look at 4 fundamental spaces, eigenvalues and eigenvectors, particularly for self-adjoint operators. So these are the things we are going to see in week 8. Okay, so before proceeding to week 8, maybe a quick break. I don't want to give an empty break. All of you know how to find eigenvalues and eigenvectors? Yes or no? Okay, so maybe one simple problem I can give you from here. Find rank nullity. So should I do give an exercise here or eigenvectors? Which exercise you want to do now by yourself? You can choose the exercise which you want to try yourself. Maybe you can do this one. You choose one. So we have already done this in class, those who have attended, but we did not do the diagonalizing those matrices part. So first of all, you need to check which one is self-adjoint. That means you need to check. What is that you need to check? Check if A hash is equal to A. Not A hash. Hermitian is equal to A. If AH is equal to A, then find eigenvalues. Okay, so find AH for each of this matrix and see if it is equal to A. Okay, if it is equal to A, find eigenvalues. Okay, so do this exercise. Meanwhile, there is a short break for me. Okay, so which of these matrices are self-adjoint?
The second and fourth.
Okay. So what are the eigenvalues? At least for one of them have you found? Maybe for this one? Sorry, I don't hear. Is anyone saying?
3,
Yeah?
3, 3,
3, 3, 3. All are 3. Are you saying all are 3?
no, 3, 3, minus.
Okay, 3, 3, minus 1. Good. So the eigenvalues for 2 are 3, 3, minus 1. Okay. And what are the corresponding eigenvectors is the next step. So before that, let us quickly look at the topics before this. Okay. Yeah. So what are operators and inner products? Operators means the domain and codomain are same, right? We know that when there is no inner product, by Schur's theorem, we at least know that there is an upper triangular representation for inner products. And here you see that the upper triangular matrix is given based on the eigenvalues, right? Here you see you have an orthonormal basis when you have an inner product. So in both the cases, upper triangular, it is upper triangularizable, right? So the next thing we are doing is that we are defining a map GV from Fn. So now GV we are defining, where is this U? U is from Fn to F. Okay, so GV is a map from Fn to F and we are defining it this way. Okay, such functions, all functions from Fn to F, all linear maps from Fn to F, they are called linear functionals. Okay, so now this is a linear functional. Okay, so for a linear functional like this, you have this kind of a matrix representation where this F1, F2, Fm are basis for orthonormal basis for Fm, and E1, E2, En are orthonormal basis for Fn. Okay, fine. So for every V in Fm, GV from Fn to F is a linear functional. So whenever you are defining something like this, then it is a linear functional. So it means what? It is a linear transformation. Okay. And the other way around. So suppose you have any linear functional, it means a linear transformation from Fn to F, then we can find a vector Wg in Fn which satisfies this condition. Okay, so what is the difference between these two? This is an inner product in Fm and this is an inner product in Fn. That is the main difference between these two. Okay, so for from this we have what is called the adjoint of a linear transformation. So how are adjoints of linear transformation defined? Inner product Tu comma V is equal to inner product U comma T star V. So T star is the adjoint of T and it satisfies this relation. Okay, so adjoint is also a linear transformation. And how do we find the adjoint of a matrix? Sorry, matrix of the adjoint operator. You simply take the complex conjugate of conjugate transpose of the matrix A, then that is the matrix of its corresponding adjoint. Okay, fine. So you know that these are the operations which we can do for adjoint of an operator. Okay, so these are some more properties here. This we have done in the session. Those who have attended the session, you know, and those who have not attended, please refer to the solution and explanation of this for the in the live session video. Okay, and in the notes as well. So I'm skipping this part. So if anyone is having doubts, you can stop me. Okay, so the next thing is that, so suppose let us say you have an operator T, transformation T from Fn to Fm, and let T star be its corresponding adjoint. Adjoint means the domain and codomain gets interchanged, right? So what is the relation we have here? null of T star is range of T perp. Null of T star is range of T perp. Okay. Same way, you have range of T star is equal to null of T perp. These two are orthogonal complements. Range of T star and null of T are orthogonal complements. Range of T and null of T star are orthogonal complements. Okay. And here we also have the fundamental theorem of algebra. Right. So rank plus nullity is equal to the dimension of the domain. So for T, the domain is N. For T star, the domain is M. Okay. Fine. So the next topic is, what are fundamental spaces of a matrix? What are the fundamental spaces? The column space, then the row space, the null space, and the left null space. Right? Column space, row space, null space, and left null space. These are the fundamental subspaces of a matrix. Okay. So find rank, nullity, and basis of fundamental subspaces of the following matrix. Okay, so let us consider an example. Just a minute, I'm picking up the question. So here let us say you have the matrix A is equal to 1, I, minus 1, 1, minus 1, 1. Okay, fine. So here, what is that we need to find? Whenever we are having a complex matrix, then what are the fundamental spaces? What are the fundamental spaces? First is the column space of A, and the next is the null space of A, and then you consider the null space of AH, and then you consider the column space of AH. Column space and null space of A, column space and null space of AH. These are the fundamental spaces. So this is sometimes called as the left null space, right? Right? And this corresponds to the row space of A bar. It looks like I striked it out. Yeah. Okay, so these are the things we need to find. So now, what is the size of this matrix? This is a 2 cross 3 matrix. Okay, so what is the rank of this matrix? Can you see? What is the rank of this matrix? Rank is 2, right? Because you have two linearly independent rows here. If you want to have a better confirmation, you can actually do row reduction and confirm it. Okay, fine. So you have rank 2, so it means the column space of A or the row space here, it should have two linearly independent vectors. So now, according to rank nullity theorem, what should be the nullity? So according to rank nullity theorem, rank of A plus nullity of A should be equal to the number of columns, right? So what is the number of columns equal to here? 3, right? So you have 2 plus something is equal to 3. So it means your nullity is 1, right? So your nullity of A is 1. So next thing we are going to see is we are going to find the column space. So what is the basis for the column space here? Yeah. Can we take the first and second column? or you can take first and third also, they are also linearly independent. Okay, this forms a basis for the column space of A. Now the next thing is that we need to find a null space of A. So for that, you consider 1 I minus 1, 1 minus 1 1, x1 x2 x3. I'm sorry, I somehow remember that I did it in this session. If I am repeating it, sorry, I forgot. Maybe I should have picked a different one. But as long as you understand the concept, it should not be a problem. This is the concept I want to tell. So you have x1 plus I x2 minus x3 equal to 0, and then x1 minus x2 plus x3 equal to 0. So these are the equations we have got. Now let us say this is equation 1 and this is equation 2. Now let's add them up. If we add them up, then we get 2x1 plus I minus 1 x2 equal to 0. Right? So it means what? So you have 2x1 plus I minus 1 x2 equal to 0. So x1 is equal to I minus 1 by 2 x2. Okay, so you can write either in this way, or you can write x2 is equal to 2 by I minus 1 x1. So either way you can write, does not matter. Okay, so if you want to write like this, it's fine, or if you want to write x2 is equal to minus 2 x1 by I minus 1. But remember, you cannot have a complex number in the denominator. So you have 2 by, here let's rewrite it as, so you have minus 2 in the top. So when it comes here, it becomes like this. So 2 by 1 minus I multiplied with 1 plus I by 1 plus I x1. So it is 2 plus 2I, and in the denominator you have 1 square is 1 minus I square. So minus I square is 1, so you have 2. So 1 plus I x1. So x2 is equal to 1 plus I times of x1. So we have to now substitute it back here. So if you substitute it back here, so you have x1, and then in place of x2 you have 1 plus I x1 plus x3 equal to 0. So what is that you have? x3 is equal to minus x1 minus 1 plus I. Okay, maybe I should write here 1 plus 1. We can simplify this actually. So you can write it as 2 plus I x1 plus x3 equals 0. So you have x3 is equal to minus 2 plus I x1. Right? So what is your null space now? Your null space is set of all x1 comma 1 plus I x1 comma minus 2 plus I x1. x1 in C. So here it is, the basis is 1 comma 1 plus I comma minus 2 minus I. So this is a basis for the null space. So what is the next space we need to find? The next thing is we need to find the null space of AH. What is the null space of AH? What is AH? 1 I minus 1 1 minus 1 1. So we need to find the null space of this, right? So null of this, how do you find? Can you tell me? How do you find the null of this? I guess it's kind of a similar process only. So should I do this, or can I leave this part? It is same as finding the null space of A, and column space of A. So now you have to find null space and column space of AH. So can I leave this or should I complete this?
Can you just quickly explain once more? Yes.
Yeah. So here to find the column space, you have two columns. So here we don't have to do anything. That is very straightforward. So for column space, here you see that column space of here AH I made a mistake. No one pointed out. So here I should have a minus I because we are taking the complex conjugate, right? So here minus I is there. So the column space of AH is simply the basis of column space of this is given by 1 minus I minus 1, 1 minus 1, 1. So this is the basis of column space of AH. Okay. Now what is the basis for the null space? For that we need to compute the null space. So you have 1, 1, I minus 1 minus 1 minus 1 times of, here you have x1, x2. So you have x1 plus x2 equal to 0 minus ix1 minus x2 equal to, okay. So do we first of all need to do this before doing this? Okay, I should have told this before computing this. What is the nullity of AH? What is the rank of AH first of all? What is the rank of AH?
Nullity of A.
I'm asking what is rank of AH? 2, right? You have two linearly independent columns, so rank of AH is 2, right? 2 elements in the basis of the column space, right? And it is a 3 cross 2 matrix. Now for a 3 cross 2 matrix, rank of AH plus nullity of AH is equal to 2. So 2 plus what is equal to 2? 0. It means what? This means that the null space of AH is simply the 0 space and the basis is simply 0, 0. Okay, clear?
Yeah.
Okay. So here are some special cases. For invertible case, you know that the null should be 0 and the range is the whole space. And for 0 operator, the null should be the whole space and range is 0. Okay. And what are left and right eigenvectors? So the usual eigenvalue and eigenvector PV equal to lambda V. So this is your right eigenvalue. So lambda is your right eigenvalue and this is the right eigenvector. Now what is a left eigenvalue or a left eigenvector? So you consider T star or AH. So the eigenvalue, the right eigenvalue of AH is the left eigenvalue of A. Okay, I'm repeating, the right, or let us say, so let us say AHW is equal to mu W. Okay, so this is the right eigenvector, right eigenvalue of AH. This means that U bar is your left eigenvalue of A. Okay, same way W is your right eigenvector of AH. So W transpose or WH is your left eigenvector of A. So if you are asked to compute the left eigenvalue and left eigenvector of A, what is that you need to compute? You need to compute the usual eigenvalue and eigenvector, that is the right eigenvalue and right eigenvector of AH. Take the complex conjugate for the eigenvalue and conjugate transpose for the eigenvector. That gives you the left eigenvalue and left eigenvector. Is it clear? How to compute the left eigenvalue and left eigenvector? Yeah?
Yeah.
Okay. So the next thing is that what is the property we have about eigenvalues of an operator and its adjoint? If lambda is an eigenvalue of an operator T, then lambda bar is an eigenvalue of the adjoint T bar. Sorry, T star. Okay. So you have complex conjugate as an eigenvalue of the adjoint operator. Okay. And eigenvectors corresponding to distinct eigenvalues like lambda for T and mu for T star, the corresponding eigenvectors are orthogonal if lambda not equal to mu bar. Okay. So the next important topic here is self-adjoint operators. It means T star equal to T. Right. So it means what? You have AH is equal to A. Right. So it means what? So you have this condition here. In particular, all the diagonal entries are real. Diagonals are all real. Okay. So we already saw some examples here. So how do you diagonalize these matrices? You find the eigenvectors, whatever is the eigenvector you find here, right? So you write them as the columns of your matrix P, right? So let's call this V1, V2, V3. Then you see that you can write P as V1, V2, V3. Then P times of 3, 3 minus 1. The other entry is 0, 0, 0. P inverse. This gives you the original matrix. Okay. So this is how you usually do the diagonalization. Right. So what are some important properties of self-adjoint operators? So for self-adjoint operators, eigenvalue of a self-adjoint operator is real. Eigenvectors of distinct eigenvalues of a self-adjoint operator are orthogonal. And self-adjoint operators are always diagonalizable. Okay, they are always diagonalizable. Okay, even though you have repeated eigenvalues, for example, here you have repeated eigenvalues, but still you have linearly independent eigenvectors. It means what? Always for a self-adjoint operator, the algebraic multiplicity and geometric multiplicities are always the same. Okay, so the same example is repeated here. It is about computation of eigenvalues and eigenvectors again. So please do this and practice it before the exam. I hope you have already done enough practice. Okay, so this finding eigenvalues and eigenvectors and diagonalizability is something which everyone should have tried at least few problems. Okay, make sure everyone does at least 2 or 3 problems, minimum 2 or 3 problems of this eigenvalue, eigenvector and diagonalization before the exam. This is for, like, you had this in quiz 1, you have it in quiz 2, you have it in n terms, so in all this syllabus you have this topic, right? Diagonalization, and it is a very important topic, right? Fine.
So could you, what is the characteristic? I mean, I didn't get the answer what was told for that problem. 3 lambda, right? 3 and 3 minus 1. So
See,
what is
I said is that, see, usually here, what is the algebraic multiplicity? Algebraic multiplicity here for lambda equal to 3 is, what is the algebraic multiplicity?
2.
2. Now, since you already know that AH is equal to A, this tells you that geometric multiplicity is also 2. This implies this. Okay, without even checking how many linearly independent eigenvectors are there, you can tell that because it is self-adjoint, it should definitely have 2 linearly independent eigenvectors corresponding to this eigenvalue. Do you understand? What is the significance? Okay, fine. So
yeah, I could understand. My question is, maybe I got that characteristic equation wrong. I mean, I'm not getting the lambda values correctly. So if you can write that equation, right? We need to solve for lambda, right? 3. The
Oh, you
lambda
want
cube.
the characteristic equation. All right, all
Yeah.
right. Okay,
I
fine.
didn't get the answer, so
Okay.
maybe I'm making some mistakes. Could you write down?
Yes, yes, sure. Let's do that. So 1, 2, 2, 1, 0, 0, 0. Right? Okay. I guess I have already done this. Let me see. So you have A is equal to 1, 2, 0, and then 2, 1, 0, and then 0.
0, 3.
I'm just checking my answer from the previous slide. Hold on. I guess I have done the same problem. Okay, so I guess the characteristic equation is lambda cube minus 5 lambda square.
I'm getting minus 15. Is that right? That's
No,
where
no, 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 it's not minus 15.
9 or else I don't know why.
Hold on. So it's characteristic equation. So determinant of A minus lambda I is equal to minus lambda cube plus 5 lambda square minus 3 lambda minus 9. This is the characteristic equation. So when you split them up, you are getting lambda plus 1 lambda square minus 6 lambda plus 9. So this is lambda minus 3 whole square. Okay, fine.
Yep, thank you.
All right. So in fact, the corresponding eigenvalues are, so for lambda equal to 3, one of the eigenvalue is 110, the other one is 001, and here you have minus 1, 1, 0. In fact, here we see all of them are orthogonal, right? Okay. Okay. So here are some properties we see. So what is symmetry? So if you have AH is equal to A, then we call such matrices to be Hermitian symmetric. Okay. So the corresponding operators are self-adjoint. In the case of real, we call it symmetric. Right? So whenever we have this condition, then the algebraic multiplicity is equal to the geometric multiplicity. Okay. So also we know that when we are diagonalizing, we will get an orthonormal basis of eigenvectors. Okay, we can get an orthonormal basis of eigenvectors with which we can diagonalize. So here, can you observe that each of this matrix, so first of all, is this matrix self-adjoint? So this is a real matrix. So you just have to check the transpose. So for this matrix, your AH is same as A transpose. So A transpose is equal to A. What about this one? 0, 0, minus 2, minus 2, 0, 0, 0, 0. So here also is self-adjoint. What about this one? Here complex entries are there, so you have to take AH. So all the diagonal entries are real, and then you have the complex conjugates here. So it is fine. So all of them are self-adjoint. So then for self-adjoint operator, you know that all of them are diagonalizable. You don't have to check whether they are diagonalizable. You simply have to find eigenvalues and eigenvectors and do the matrix P and P inverse. Right? Fine. So orthonormal matrix and similarity. So what is this concept here? So what are orthonormal matrices? So orthonormal matrices are matrices which satisfies this property. Okay. So such matrices are orthonormal matrices. Okay. So here one thing you see that from here SH is equal to S inverse. So S inverse AS is the diagonal matrix here. So for a self-adjoint matrix, you get an orthonormal basis, and hence the columns are orthonormal here. Okay. So in that case, you get SHS is equal to I, which is equal to SSH. What is happening here? Do you understand? See, for whenever we are having a self-adjoint operator, the eigenvectors are orthonormal. Orthonormal means now each of this entry here is an orthonormal vector. So the columns are consisting of orthonormal vectors. So if orthonormal is there, then when you are taking the complex conjugate, then again you see the rows are orthonormal, right? So when you are doing the matrix multiplication, you can easily see that all the diagonal entries are 1, the other entries are 0. Because of the orthogonality, the non-diagonal entries are 0, and because of the normality, the diagonal entries are 1. Okay, so this is something special about self-adjoint matrices. See, whenever you are given, what is one advantage? Everyone please listen this part. Suppose you are given a self-adjoint matrix. Usually what you do, you find the eigenvectors V1, you find the eigenvectors V1, V2, V3, right? And then you form the matrix P, which is V1, V2, V3. Then you find what is P inverse, right? But in case you have a set of eigenvectors which are orthonormal, then what do you know? Your P inverse is simply PH. Okay, so you don't have to do much calculation. It is very straightforward. Okay, so whenever you have A equal to AH, you can find an orthonormal basis, and if you are able to find an orthonormal basis of eigenvectors, then you simply have to find SH you don't have to find S inverse. Okay, is this point clear? It saves you some time. Yeah. Okay. Remember, see, you don't assume that for a self-adjoint operator, automatically you will get orthonormal basis. For example, here, this is self-adjoint. So whatever you got is orthogonal. So the next step is you have to divide by its norm. So how to convert a orthogonal set into an orthonormal set? Tell me quickly. So you have V1, V2, V3. This is an orthogonal set you can see. How to convert it into an orthonormal set? So this is orthogonal. How to convert it into orthonormal set? So to make it orthonormal, only one step is required. So you take V1 by norm V1, you take V2 by norm V2, and V3 by norm V3. Now this is an orthonormal set. Okay, now for this, you don't have to calculate the inverse. You can simply take the complex transpose, conjugate transpose for the inverse. Okay, so for self-adjoint, you will get an orthogonal set of eigenvectors, which you have to further convert into orthonormal to apply this property, which I mentioned it to you. Clear? Yeah? All right. So the last part is this orthogonal decomposition. So here we are just stating, we did not do many problems. So this is just something you should just know, that for an Hermitian matrix, you have this kind of a property that you can split them into sum of each of this is now an matrix of rank 1, right? You have this kind of an orthogonal decomposition where each of these vectors are orthonormal. Okay, so I guess this is the last slide. Yeah. So what are the main topics in week 7 and week 8? Quickly, let me tell you. So in week 7, you see in this is about inner product spaces, right? So mainly you have problems which tells you to find the set of orthogonal vectors to a given set of vectors. Then you have the process of Gram-Schmidt process, which converts an set of vectors basis to orthonormal basis, right? And then you have finding least square solutions. So you have uh, finding WPERP. So I'm just talking where you have more problems. Finding WPERP, and here, yeah, this is Gram-Schmidt orthonormalization, least square solutions. So finding WPERP is here only, right? And then finding projections. So these are the places where you have lot of problems. Same way in week 8, you have plenty of places where you can, so finding adjoint, so finding Rees representation. I did not do Rees representation here because I did that Rees representation part elaborately in the live session, so I skipped it here. So please refer to the live session if you want for finding Rees representation. And then finding adjoint of an operator, right? And then 4 fundamental spaces, finding eigenvalues and eigenvectors. And for eigenvalues and eigenvectors, remember you have right and left. So whatever is asked, depending on that, you should find. And then you have what are called self-adjoint operators. So for self-adjoint operators, you have diagonalizability, right? So A is equal to P inverse dP, but P inverse is equal to PH if the columns are orthonormal. Okay, so these are the key points for week 7 and week 8. I hope the session was useful to all of you. So in all the best for tomorrow's exam. Okay, whatever topics you are clear with, please concentrate on that. Don't put too many things at the end. So whatever concept you are very clear, do problems there. Don't confuse yourself at the last moment. Okay, fine, all the best.
Thank you.
Thank you everyone.
That's a good session, useful.
Thank you, ma'am.
Yeah, thank you.